7.4 estimating, a little bit going deeper, I guess. Okay, so in this section, we will now have two sets of data. So that's really all this means. Your mu from one set of data and your mu from a second set of data. So we're going to estimate the difference between their population means. It's similar to section 7.1 and 7.2, but the conclusion is a little different. Independent samples. When a sample drawn from a population is completely unrelated to the selection of sample data from another. We talked about that in the beginning of this class. Dependent samples, when each data value in one sample can be paired with the corresponding data value in the other sample. We will be confining our study to independent samples, really. So your X1, X2, like I said, the ones and twos, it's just good to understand that it looks all really similar, but it just means the first set of data and the second set of data. Everything else should look familiar to you in terms of symbols. So the ones and twos are just to distinguish between the two sets of data. When samples and your sigma is known. So remember, we're always like when things are known and when things are not known. So it is known. We're going to be using that z-score still, just like we did before. When it was known, we used the z-score, not a t-score. But here's the formula for that. And then our confidence interval level, it is a little bit more math. We don't just add and subtract our margin of error. We have to subtract the two means and then subtract the margin of error. Okay, so the difference between those, that's what we'll always do. So let's go ahead and just turn the page. So like all of this is the math you'll do to find your lower limit. Okay, and then you have your less than symbol. And this will always be in between just to represent the difference between the two means and then your upper limit. Yeah. Let's turn the page. So, but the conclusion, this is the different part. We don't care about the numbers really so much that we end up with. All we really need to know or look at is the signs of the numbers. So if when you do all that math, both of these are positive, like I said over here, after you do this math that we're going to be doing, like if you did all this math and it's positive, you did all this math and it's positive, we can always say that mu1 is larger. So the data set, the first data set's mean is larger. If they're both negative, then we're going to say that mu2 is larger. Now, if one's negative and one's positive, it doesn't matter. Well, I mean, yeah, one's negative, one's positive. Different signs, I guess is what I was trying to say. There is no significant difference is what we're going to use terminology, specific terminology that you need to get used to hearing and seeing that there is no significant difference. And so how do we apply this? Let's move on to comparing Duracell and Energizer batteries. So Duracell, we're going to consider mu1. Energizer, we're going to consider mu2. And they give us some values. There's maybe they sample 42 batteries, and if the sample that had an average of 9.8 hours of power. So we're looking to see what one lasts longer with a standard deviation of 2.2 hours. But Energizer, we only checked 38 batteries with a mean of 8.1 hours, and it had more of a standard deviation of 3.5 hours difference between that. So find a 90% confidence interval for the population difference of that between the two mu's, two averages of lifetimes for these batteries. So our Z sub C value, that's gonna be looking at the, 90% value. I'll put that above. You're gonna be looking at the 90%, so our Z sub C is 1.645 from that table. So to find our margin of error, what you're going to do is use that formula from above, and I'll write it down right here this one time, but otherwise you need to refer to that page before. You're gonna take that Z sub C value and we're gonna multiply it times a lot happening underneath this radical. So the standard deviation squared of however many there were from the first samples, all those subscripts mean, and the standard deviation looks like a 6, but it's not. This means standard deviation from the second, which would be the Energizer values, and how many were in that sample. So in that, you're gonna say this is 1.645 times the standard deviation from my first set of numbers was 2.2 hours squared over 9.8. We're going to add that to standard deviation 3.5 squared over our mean of 8.1. I'm doing my mean. This is supposed to be number in the sample. That's why I paused. Sorry. Sometimes I make mistakes. I'm human. So our standard deviation over number in sample. So 41 and 38. This is the 4th video I recorded today, so maybe I need a break after this. All right, so we're going to take this times all of that in our calculator, and I do like to show you at least one, so I'm going to, again, highly recommend pausing the video, trying it yourself, seeing if you get what I get. This, I'm separating the fractions just like I do in the formula underneath the radical. It's going to look kind of long and busy, but that's just what it will be. And arrowing out from all that, you're not going to be able to see the entire formula unless you just arrow back over. You can kind of double check what you typed in the beginning from space to space, but it takes a little bit to kind of get over there. You don't have to check it, but it doesn't hurt to just double check your entry. So when you figure that and round, we'll get 1.09 would be our margin of error. So I guess I could write that right here, 1.09. Could have done all that math over here. So our intervals would be subtracting our X bars, finding the difference between them, and then subtracting that margin of error that we just found for the lower limit. So 9.8 minus 8.1, and then we'll subtract, after we do that, we'll subtract 1.09. So that's going to be, when you plug all of this into your calculator right here, you're going to get 0.61. And then we would write is less than U1, U2, the difference, this just means the difference between those two, which is less than. Now we need to go find our upper limit. So I'm going to write lower here and upper, just to kind of help with organizing our paper. So our upper is just doing really the same thing at the beginning, subtracting your means, but then now we're adding our margin of error. So 9.8 minus 8.1 plus 1.09. So once we do this, I don't know that I should be boxing it out. I'm not meaning to like say that's my answer. I'm just drawing attention to this is the math you'll plug into your calculator, and you'll get a 2.79 value. So these are, let's highlight it. These are the lower and the upper limit in the levels. But remember, so we're looking at this and we have to make a conclusion now. And so this is a positive number. And this is a positive number. So what we do is we go back up here, and if they're both positive, then we can determine that mu1 is larger. So I'm gonna write that just to the right, or maybe to the left, because it's gonna help us write our conclusion. So if the mu1 is larger, what that means is Duracell has a longer average life, lasts longer than Energizer. So we would say, since we're talking about mu1, and remember mu1 was Duracell, that's why we labeled it to remember. I'm 90% confident the average life of Duracell is longer than Energizer. Okay, now, like everything we do, now we're going to say sigma is unknown. And that just means that you're going to be using your t-table. That's the only difference. Okay, everything else is the same. We learned about finding the degree of freedom, so we can't go find that t sub c value. So let's move on. Assume absorption times are normally distributed. Find 90% confidence interval for the difference in the average absorption time for two drugs. So we're talking about Tylenol. So we're going to call that mu1, and Advil, we would call that mu2. So if our confidence interval is 90%, that's going to be your 0.900 column. And you have to know your degree of freedom by taking the smaller sample. So I don't know that we've talked about that. That's why I'm pausing, but whatever the smaller sample size is, in this case, it's 8. We will use that one. So 8 minus 1 is 7, and that's going to give us our confidence interval level. So you'll have two things, and they would have probably two different sample sizes. So always use the smallest one. So we're going to go to 7, and we said 90%. So it looks like it's a 1.895. We have to do that work to find that number so we can plug that into our formula. So 1.895 times, then we have the square root of a lot going on. So we're taking, it's just the S value, but it represents the same thing, standard deviation squared divided by how many were in that sample, which were 8, plus standard deviation of the second group squared divided by, it had 10 in its sample. You're going to plug that into your calculator, and you're going to round to 3.56. Pause the video and make sure you can do that so that when you use your numbers and values, you know you're not having a calculator error. So our interval, we're going to take 24 minus 29, so subtracting our two means, and then I'm going to subtract that interval level, or that margin of error, 3.56, and we would get negative 8.56. So that's going to be less than our mu1 minus our mu2, basically the difference in the mu's. And now we're going to add it this time. So we did all this math right here to get that number there. And so now I'm going to do 24 minus 29. And I'm going to add 3.56. Okay. And then when you do that, you're going to get a negative 1.44. So again, what does this mean? What we look at is that they're both negative numbers. That's a negative number, and this is a negative number now. And I'll just use number symbol instead of writing it out like I did before. So this time, mu2 is larger, right? Because if they're both negative from before, they're both negative, then we could say mu2 is larger. The second set of data would be better, basically. It would have a longer absorption time. That's a hard word for me to say, I guess. I'm 90% confident the average absorption time for Advil is longer than Tylenol. Now, we're not really comparing if one number is bigger than the other or anything, but we're comparing these two things to see if they're both negative, and that tells us that mu2 is larger, meaning it would have a longer absorption time in this application problem. So now we're kind of doing the same thing, but we're talking about proportions. So we're working with those P's, which takes us into the p-hats that we just learned about in the previous lesson. So consider 2 independent experiments, binomial experiment 1 and 2. And so everything is all the same except for you have subscripts to show the difference between the 2 different experiments. All of this is the same, again, except for we're talking about the 2 experiments. Okay. That is finding that the probability of successes or the failures times however many there were, when you do those math, it's greater than 5. Same thing with the second set of data. We'll be using our Z sub C score, our value, and then we're still doing a lot of what we did when we were talking about probabilities under the radical. We'll be doing this math like we have before to compare and decide if they're both positive, both negative, or one's negative and one's positive, and what that means with our conclusion that we've learned that's different. So let's look at this example next. So gender and the use of turn signals. So does your sex determine if you use your turn signal or not? A statistic student wanted to find out whether gender and the use of turn signals when driving were independent. When absorbing the first group of people, which were men, 936 of them, 585 used their signal. While observing the women, so that's the second, the subscore 2 represents the women. They looked at 607 and 452 of them used their turn signal. We want to find a 95% confidence interval. So we have to do it separately for men and women both. So we have to do it kind of twice. So men, we said that there were 936 men that they observed and they used their turn signal, was considered a success. So 585 of them did that. So our P would be taking 585 divided by how many were sampled, which would be 0.0625, or you could call that 62.5% of men used their turn signal. Q hat would be subtracting that 1 minus 0.625, and so 0.375 or 37.5% did not, is what that means. Women, and it just say what percentage of men use their turn signal and what percentage of women. So we would be answering here. Percentage of men used it was 62.5. But we went ahead and did the Q hacks. We have to use them in our calculations. So really they were just looking for this for men, and now we need to go find our women. So they sampled 607 women, where that's 2s, not 1s, where they said 452 of them used their signal. So to find P hat, we take 452 divided by 607, and we get 0.745. So to answer that as a percentage, we'd say 74.5% of women use their turn signal. And so our Q hat would then be taking 1 minus that, which is 0.255. Or 25.5% didn't. So if we're doing our margin of error, we need to remember that they told us that we're finding a 95% confidence interval. So you go look at that 0.95 on your Z sub C table, your Z score table, and that's 1.96. Or on our Z table for this one. And then we get to do our math where we do our Z sub C times the square root of all that's going on underneath that radical. The formula's on the other page if you need to look at it. We're going to be taking, for men and women, and we're going to be adding that together, right? So our P hat for men was 0.625. You need to use the decimal form. Times our Q hat was 0.375. And we divide it by how many were sampled, which in this case was 936. So there's a lot happening. So that's one fraction plus another fraction, and that's going to be the women values. So 0.745 times 0.255 divided by 607. Takes a long time to kind of write that out probably, but you need to organize it, make sure you have it all down. Also, when you're submitting your work to me, or if you have an issue plugging it in and you think it's right, but you've done something wrong, I need to see the work to be able to give you credit for it. So you need to write it down. Don't just type it in your calculator. So underneath there, I am going to go ahead and type this one in just because there's a lot of values in this one as well. You should pause this and try to type it yourself. I know it's really similar to the one before, but it is a little different. So I thought I would go ahead and take the time, buff it forward if you don't wish to watch me typing this in. Again, typing errors. Make sure your parentheses on the outside of all of that, not just down there in the lower half where you get an error. So our margin of error here is 0.047. So confidence interval, what this means is you're going to be taking our success of our men, 0.625, minus the success of our women, 0.745. Instead of X bars, we use those probabilities, those P hats. You're going to subtract that, and then you'll subtract that margin of error. And that's going to be less than your P1 minus your P2. Just going to kind of write it all out to kind of help you. And then we'll do the values. We'll do the math. 0.625 again minus 0.745. So what's happening in the first steps of both of these are exactly the same. The only difference is we're adding the margin of error in that. And that's what gives us our confidence interval. So you're going to get a negative negative 0.167, which is less than the difference of our P's. And then when we do that one, you're going to get a negative 0.073. So what we notice here is they're both negative numbers. So what does that mean? That means mu2, or in this case P2 is larger. Okay, so we would say so we're talking about women, that was our P2 value. And if it's larger, that means they use their signal more often. So I'm 95% confident the proportion of women using their turn signal is greater, larger, higher. In this case, I would say, if we're talking about that, it's more likely or something, but I'll just put is higher. Women using their turn signal is higher than men. Meaning the percentage of the women using their turn signal would be higher than the men's percentage, even though we kind of could see that even in the very first step. Just remember, we didn't really have an example in this case that if one is negative and one is positive, then we would just say there is no significant difference. So you really couldn't make a determination on maybe which one was better than the other, like in terms of Duracell batteries. If one was negative and one was positive, I couldn't say that one was necessarily better than the other. And that's what there is no significant difference means when making those conclusions, if you come across one like that.